Kevin, are you ready? Let's start.
Yes, I am.
Okay. Hello, good morning. Welcome you again to this Water, River, and Delta System Source to Think webinar series. Today, we invite Professor Kevin Xu from Louisiana State University to talk about the Mississippi River Atchafalaya River, the sediment transport along the Louisiana coast. So once again, this coming Friday, Professor Courtney Harris from Virginia Institute of Marine Science, she also talked about sediment transport, particularly focused on numerical modeling for the large river system from the Pearl River, Adriatic Sea, Mississippi River in Gulf of Mexico, and the Ayeyarvady River in Andaman Sea. So I think this week we are kind of shifting a little bit to the numerical modeling part. I think it's fantastic, given the last week Sam Batley's talk about the Mississippi River. Today, we were here, and also this week we will hear, more Mississippi River related talks. And Kevin, originally graduated from Ocean University of China, then got his bachelor and master degree over there, then went to Virginia Institute of Marine Science, studied with Professor John Milliman, got his PhD, then working a little bit at Coastal Carolina University in South Carolina, then moved to Louisiana State University. Now currently he's also a deputy director of the Coastal Study Institute. His research mainly focused on geological oceanographer, but a little bit more for that dynamic part, combined both observation and the numerical modeling. And he published many papers with more than 10, 14 students, and also the chair of that education and knowledge transfer for the community surface dynamic modeling system, and also associated editor S2S20 Coastal and Shelf Science. Okay, Kevin, now it's your turn. Please share your screen and put a presentation mode.
Thank you, Paul. Let me share my screen.
Good.
Okay, can everyone see my screen?
Yeah.
Yep.
Okay, great. Well, thank you, Paul, very much for hosting this wonderful webinar series for all of us. So the title for my today's talk is the Dispersal of Mississippi and Atchafalaya Sediment on the Louisiana coast under the climatic and anthropogenic impact. So I would like to begin with a diagram from NSF Margins Source to Think program. I believe most of you already know this diagram. So in this conceptual diagram, there are mainly three systems: the terrestrial part, which is on the land, the coastal part, which is along the boundary between land and ocean, as well as the marine part. So on this diagram, there are many different kinds of processes. For example, the longshore currents and waves can mobilize the sediment, and the storm can impact the inertia of the sediment transport. You also can have gravity flow and some other processes to impact the preservation of the sediment. In my today's talk, I'm mainly focused on the coastal part, which is mainly in the base and the inner continental shelf. And the spatial scale is relatively focused on the coastal region. And regarding the temporal scale, this will be mainly focused on a relatively short temporal scale, mainly from years to months to days. So I would like to borrow a diagram from Dr. Don Wright and Chuck Netrawer, who published this diagram 25 years ago on estuaries. So there are mainly 4 stages in the dispersal of river sediment in the sea. So when a river carries sediment to the coastal area along a short perpendicular transect, The first stage would be the supply by the river. Stage 2 is initial sediment deposition. Stage 3 would be the resuspension and transport by waves and currents, which is 3A, or it can be by slope failure process, which is 3B. So 3B is kind of a very unique process, and in my view, it has been understudied, but lots of people have been studying, for example, submarine landslide or gravity flow, which are all relevant to the slope failure process. And then stage 4 is the long-term net accumulation. And although this diagram is very conceptualized and simple, keep in mind the actual sediment transport in the coastal area can be more complicated. Stage 2 and 3 can be repeated multiple times before you can reach stage 4, which is the long-term net accumulation. So here in LSU, I lead a lab called the Sediment Dynamics Lab, and this is our logo. In my lab, we use 3 contrasting but complementary methods to study sediment dynamics. So the 3 methods include numerical modeling, tripod, as well as geophysics. So in numerical modeling, we have been mainly using regional ocean modeling system, ROMS, to study 3D sediment transport and deposition. And then regarding the geophysical method, we have been using subbottom, side scan, and bathymetry to look at the morphology and the dynamics of the seafloor. In terms of the tripod method, this is mainly focused on bottom boundary layer. We have been using all different kinds of optical and acoustic sensors, including ADW, ADCP, OBS, ABS, wave gauge, among others. So last Friday, Dr. Sam Bentley gave a wonderful talk about the Mississippi source to sink system. And this diagram is in a log scale in the style of Dr. J.R. Switzky and my PhD advisor, John Milliman. So I really love this diagram. So for my today's talk, I'm going to focus on the lower left side, which is in this red oval. So regarding the time scale, I'm going to look at from yearly change to monthly to daily change over here. Regarding the temporal scale, I will be focusing on a relatively small spatial scale from, for example, millimeter sediment erosion deposition on the seabed up to hundreds of kilometers of sediment dispersal on the shelf. So there will be a total of 5 parts in my today's talk, and I organize those parts using right nature hour conceptual diagram. So the first part will be mainly about sediment suspension. So in this part, I use a device to collect the sediment cores and measure the sediment erodibility, and try to measure how erodible the sediment is on the seafloor. And then I will look at the slope failure process on the Mississippi River Delta front. And this is also related to map twisting. And then the third part will be focused on the sediment settling, resuspension, and transport using 3D ROMS model. After that, I will talk about the climatic impact. In coastal Louisiana, we have 2 major weather systems, well, 2 large energetic weather systems. One is, as you probably know, the hurricanes, right? So this past summer, at least 7 or 8 major hurricanes made landfall in the northern Gulf of Mexico. This is a very unusual and historical record in our area. But for my today's talk, I will be talking about Hurricane Katrina and Rita in 2005. And then in winter, in coastal Louisiana, we have typical cold fronts. So every 3 to 7 days, we have those moderate but frequent energetic events passing coastal Louisiana, which can transport sediment. So the last part of my today's talk will be related to the sediment dredging. So as you probably know, Louisiana is facing a huge land loss problem. So people have been dredging sand and mud. And then after you remove lots of sand, you have a large dredge pit, which can facilitate the sediment infilling. And this is also related to the long-term net accumulation of the sediment. So part one, sediment suspension. So here I would like to introduce the device I have used. So we have been using a system called a Roost erosion microcosm system. So this study was funded by NOAA, and the lead PI was Steve DeMarco from Texas A&M. So Tom Bianchi, me, Carney, and Rob Hetland are all involved. So in this project, my role was to look at how sediment resuspension impact hypoxia. So we have used a total of 3 different coring devices to collect the in situ sediment core from Louisiana shelf. And then we transfer the core to the lab on the research vessel. We started the experiment immediately. So right above the core, we have water, and then on the top, we have a spinning disc, which is controlled by a control box here, which is then connected to the laptop. So when we control the rotation speed of the spinning disc, we can actually control the shear stress we can apply on the sediment core, and then we use the turbidimeter to measure the resuspended sediment. So this is the flow-through system. So for this research, we mainly focus on stage 3, which is the resuspension part of the sediment. So here is how the device works. So we have a total of 7 different levels of shear stress applied on the sediment core. And when we control the spinning rate of the disk, we can actually have a very accurate estimate on the level of shear stress we apply on the sediment core. So after the clearing of some turbid water on the sediment core, and when we apply a high shear stress, that normally trigger the resuspension of the material. For this sediment core, when we apply 0.2 Pascal, you can actually see a spike. And this can be regarded as a critical shear stress to trigger a significant sediment resuspension. So more details are in my paper published on ECSS in 2014. So let me step back. So for each experiment, we collected 2 cores at one site, and then we prepare the device, and this measurement takes about 2.5 hours. After that, we do the filtration to get the eroded mass. So the total time needed to finish 2 cores in one station is about 5 hours. And now let's take a look at the result. So here we have lots of bar diagram to show the eroded mass when we apply a shear stress around a 0.4 Pascal. Each bar here represents at least 5 hours of field work, including core collection, measurements, cleaning, filtering, and lots of other kinds of work. So the diagram is a little bit busy, but we were able to collect the data during a total of 5 research cruises in 2010 and 2011. Panel D is a very special research cruise in which we collect a lot more sediment core, and this was in collaboration with JP Walsh and Red Corbett. And we were funded by NSF Rapid program to do some measurement. So to put all the data together, we have a summary diagram over here. So you can see we apply a higher shear stress, you start to erode more and more sediment. And this black curve over here, based on our knowledge, is probably the first reported erodibility curve in the Louisiana shelf. We established a relationship between the eroded mass and the shear stress you apply on the on the sediment core. So that was part one. So now let's move on to part two, which is slope failure. So on right nature hour diagram, this is actually the 3B, stage 3B. So our study area is on the Mississippi Delta area. So this is the birth delta. Here is the Southwest Pass. And then we were able to gather a total of 3 bathymetric data sets. So in this region, the 2005 is actually the bathymetric data from JP Wash, which is post Katrina. And then we will also be able to access data collected by Fugro in 2009, which is in green. And then LCU CSI collected new data in 2014. And this work was led by my former PhD student, Jeffrey Obels, and we published a paper on 2017. So to the right, we have a map to show the difference of the depths between 2005 and a 2009 data set. So everywhere in yellow indicate very small bathymetric change. Everywhere in red, however, indicate a rapid deepening of the depths, okay? So each letter G over here indicate a submarine gully, which is a topographic low. So you can say in the shallow water, which is between 20 and 35-meter water depths, between 2005 and 2009, and this was actually a relatively low energy period during which no hurricanes passed our study area. And we found an amazing 1 meter or sometimes even 2 meters of deepening of the submarine gullies, okay? So this study highlighted that the submarine landslide might be much more active than many scientists thought previously. Even during an intermediate or low energy condition, the submarine gully is still active and you can still transfer a large amount of sediment from the shallow water into the deeper part of the water. So here I have 2 slides to show some really beautiful and unpublished data. So in 2015, we collected bathymetry and side scan data. So this is in the shallow water going from probably 20 meter to 40 meter deep. And the orange here you see is undisturbed, smooth and flat seafloor. And then here are the complex 3D feature of those mudslide gullies. And the side scan map also shows some beautiful features. So you can actually see relatively low reflectivity from the gullies because those are disturbed sediment. And the side scan map also can show very clear geometry, especially the edge of those stair-shaped mudslide gullies in the Mississippi River Delta front. So our study area is focused on the offshore area southwest of Southwest Pass, and this is the Mississippi Delta. And using this 3D diagram, you can actually see there are lots of active gullies over there. But in fact, there are numerous submarine gullies or submarine landslide in the subaqueous part of the Mississippi River Delta, especially near the outlet of the South Pass and near the area of the Pass Lotra. So when you have those active sediment movement, those submarine landslide can actually be very major geohazard to the oil and gas platforms in this area. So now we covered the erodibility, we covered about stage 3B, but now let's take a look at stage 2 and 3A. So basically, initial settling of river sediment, as well as resuspension by wave and currents. So back in 2007, I worked with my postdoc advisor, Courtney Harris, to start working on the numerical modeling part. So we collaborated with Dr. Robert Hetland from Texas A&M. So this is the model grid we used, which was developed by Rob. So the model grid cell is about 5 to 10 kilometer resolution. Our main focus is on the shelf. And as you probably already know, along the 20-meter isobase, this is the region in which you tend to develop the hypoxic water in the summer. So the focus of this numerical model is on the shelf. And I was able to add a river sediment into the model, and I added spatially variable seabed sediment onto this model. And we also get some wave data from Jim Calhato from Texas A&M. But keep in mind, our resolution is about 10 kilometers. And we did not include those coastal bays or estuaries because that was not our focus. And we also did not include tide. So if you look at the morphology of the Louisiana shelf, along the eastern side, we have the Baritory Delta, we have a narrow shelf. And then along the west side, we have a Atchafalaya River. This is the Baritaria Bay, and then you have a flat and a broad shelf. So if you compare those profiles along eastern and western side, they are quite different. So this is a topographic profile comparison. It's very clear that if you are offshore of a Mississippi River, this is much, much steeper, probably 5 times steeper than the Atchafalaya shelf. And those two shelves are very different, and they are controlled by contrasting processes, which impact the sediment transport. So we were able to compare our numerical model with some sediment accumulation rate measured by different researchers. For example, near the Mississippi Delta, you would see really focused and circle-shaped sediment accumulation. So the depot center is right offshore of Southwest Pass, and the high accumulation rate can reach 5 centimeters per year, and then it decreases rapidly offshore. And so our model result in blue agree very well with some cesium-137 measurement from Mead-Allison 2007. And then on the Atchafalaya shelf, this is the model, the sediment accumulation rate in the year 1993. We modeled the year 1993 because this was a large hypoxic water year. So that's our focus. And then here we have some published data from Amy Drott in 2005, and they used latitude 10 to quantify the sediment accumulation rate. So regardless the spatial difference, in general, if you are very close to the river source, you have centimeter per year level of sediment accumulation. And then if you are relatively far from the source, it will decrease to millimeter per year of sediment accumulation. So, so we ran the numerical model, we did a validation, and we also did some model sensitivity test. So I have 3 panels to show the sediment accumulation in the year 1993. And keep in mind, we are focusing on stage 2, which is initial deposition. So in the top panel A, we used a fast settling velocity, 1 millimeter per second. In the middle panel, we use a settling velocity of 0.1 millimeter per second. And then in the bottom panel, we use the 0.01 millimeter per second. And this is very intuitive. If the sediment settle to the bottom very quickly, they cannot travel very far, right? So because of that, in panel A, nearly all the sediment just deposited right next to the source, no much dispersal. And if you look at the color bar, again, this is the log scale from 10 to second to 10 to -4. This is the 6th order of magnitude, which is a huge, huge difference, okay? So based on the model sensitivity test, we believe that over a year time scale, the sediment coming out of those 2 rivers should be like a panel B, which is in the middle. In other words, you can still see high accumulation near the Baritory Delta, and then offshore of Baritaria Bay. But you should be able to see some small but measurable sediment accumulation far from the source. And then here we have 4 panels to summarize what we found for the year 1993. Panel A shows very strong westward longshore currents, fresh water coming out of 2 rivers, clockwise gyres west of the delta. And then panel B shows high near-bed wave orbital velocity, which is very important for sediment resuspension, especially on those submarine sandy shoals. And panel C shows wave height decrease onshore, and there's also sheltering effect behind the very islands. And then panel D shows depth integrated long-term average suspended sediment in the water column for the entire year. Okay, so after our work for the model year 1993, we use the exact same model, and we start to look at the impact from Hurricanes Katrina and Rita. So as you probably know, those 2 hurricanes are probably the 2 most devastating hurricanes in Louisiana history. So they happened in the year 2005. Hurricane Katrina made the landfall in late August, and about 1 month later, Hurricane Rita made the landfall in western Louisiana. And so we ran the numerical model, and the challenge we had to deal with is actually the extreme conditions. It's very, very unusual, and we had to deal with lots of huge numbers. Just to give you an idea, over here, during the peak of Katrina, 25-meter tall waves. Okay, that's a huge number because on average in Louisiana shelf, you only have a half-meter wave or 1-meter wave, low energy. And then if you look at the near-bed wave orbital velocity, 3 meters per second wave orbital velocity on the Louisiana shelf. So this is a huge, huge condition during which lots of sediment can be resuspended. One main effort in this paper was to quantify the erosional rate, and we did lots of sensitivity tests, try to figure out what kind of a erosional rate is a reasonable value we can use. And then I also want to emphasize we had to deal with asymmetrical wind field. In Northern Hemisphere, when you have a hurricane passing your study area, most likely the strongest winds are not in the middle along the eye of the hurricane. Rather, it's a few kilometers to the east of the track line of the hurricane. Okay, so this is the region you tend to get the biggest erosion, you have the biggest disturbance. So it's an asymmetrical wind field you have to deal with. So now let's take a look at those 2 hurricanes. We have Katrina on the left, Rita on the right. And over here, we have the wind field, and you can actually see the wave height. As I mentioned, 20-meter tall waves, really big ones. And then on the bottom, you can actually see huge bottom shear stress and very high sediment concentration. The model of the sediment concentration was reaching 20 kilogram per meter cubic. And this is almost 20 grams per liter. So I don't know if you know this, but if the sediment concentration is over 10 grams per liter, that's called fluid mud. But in our model, we did not model fluid mud, okay? So we were able to model very high concentration, but we did not include sediment concentration induced stratification, for example. And then during Rita, you can again see the counterclockwise wind field, and you can actually see lots of sediment resuspension from the shelf. I also want to draw your attention to this area. So you can see we have plenty of red, but here is green or blue. Here is green and blue. So the reason we did not have much resuspension was mainly due to much coarser sediment, mainly the sandy material on top of those submarine shoals. And then we were able to quantify wind speed, shear stress, and seabed elevation change in multiple locations. And remember, our research objective was to look at how sediment resuspension impact hypoxia. So we picked 4 stations along the 20-meter isobas, including AC, 10B, AB5, and a station offshore of the Birdfoot Delta. So if you study hypoxia, you probably already know those 3 station names. So during Hurricane Katrina, we had 50 meter per second winds. Shear stress reached almost 50 Pascal. This is extremely high. And the sediment erosion was reaching 1.5 meters. So this is huge. And then we also have Hurricane Rita, which also impacted all 4 stations. So the take-home message for this paper is that it really depends on where you are, how strong the hurricane is. And if you are east of the hurricane, if you are very close to the track line, but you are east of it, and then if the hurricane brings you a very high wind speed, and if the hurricane is moving at a very slow speed, those are the conditions in which you will trigger the biggest sediment disturbance on the seafloor. Okay, so after those 2 modeling work, I want to introduce a more recent modeling work in collaboration with Dr. George Xue's group. We focused on the year 2017 and 18, and we used a much higher model grid resolution. So in this model, we used a 0.5 kilometer resolution. We included all the bays and estuaries. We included the tide. We also tracked the sediment coming out of the river, as well as the sediment in the inner and outer continental shelf. So here is our new modeling result. So in this model domain, we focus on Atchafalaya Bay, Terrebonne Bay, and Ship Shoal, which is a large submarine sandy shoal. So on the panel A, we have the surface salinity. You can definitely see the freshwater input from Atchafalaya, but not much freshwater to Terrebonne Bay. And then the mean currents are moving to the west and to the south. And then you start to see some detailed features on the nearby wave orbital velocity. For example, on top of Ship Shoal, you start to see high wave orbital velocity due to the shallow water depths. And you also start to see some fairly big wave orbital velocity just seaward of the Barrier Islands. And then we have the peak wave height over here and suspended sediment in panel D. So now let's take a look at the long-term net accumulation. So we have 2 panels. Panel A shows the sediment deposition coming out of the Atchafalaya River in the year 2017 and 2018. This was not a 2-year model run. Instead, it's actually a 15-month period. Not a surprise, lots of sediment deposited right next to the delta. And then we have sediment accumulating on the inner shelf. But we also saw a very interesting patchiness in this entire study area, okay? So if you take a look, we start to see some really, really interesting area in which you do not have much sediment deposit. And those are probably related to the shallow depths of the submarine shoals, or maybe some areas surrounding those headlands, okay? So those kind of patchiness was not seen in our previous modeling study. This is new. Another thing I want to emphasize is that although most Atchafalaya sediment moves to the west, right? This is a very well-known long-term net sediment transport. If you take a look, not much sediment on top of Ship Shoal due to the energetic environment, but we still see a trace amount of sediment southeast of Ship Shoal. And if you convert this to convert this to the sediment accumulation rate, this is probably close to a millimeter per year of sediment deposit. So this indicated that over the 15-month period of time, in some period, the Atchafalaya sediment can escape from inner shelf to the deeper part. They can also bypass the energetic Ship Shoal and go to the southeast side. This is a new finding. And then we also use lots of sediment tracers to look at the sediment from the inner shelf. What we did was we actually divided the seabed sediment into two categories, shallower than 5 meter isobase and deeper than 5 meter isobase. We run the model, and then at the end of the model run, we trace where are the shallow water sediment, i.e. shallower than 5 meter. So it's very interesting to see that we were able to find lots of sediment moving from inner shelf to the deeper water. Okay, so here in yellow, the amount of sediment is probably close to millimeter per year. So this indicated that although the river sedimentation in the middle Louisiana shelf is minimal, if you do a latitude 10 study, if you do a beryllium 7 study, you probably get a 0 river sediment accumulation. But the inner shelf is pretty dynamic, okay? We saw very strong inner shelf, middle shelf sediment exchange under this kind of environment. Okay, so after numerical modeling study, I want to talk about cold front impact. For this part, I would like to talk about tripod bottom boundary layer observations. As I explained, we have been using many different type of optical and acoustic sensors to study the sediment dynamics, and tripod is a very powerful tool we can use to study those short duration energetic events. So on this diagram, I show many study areas. In the next several slides, I'm going to focus on two bay areas. One is Fall League Bay, which is southeast of Chapalaya River mouth. The other is Baritory Bay, which is an abandoned deltic system, and it's been eroding at a very fast rate. So LCU is here. This is New Orleans. Ship Show is over here. I mentioned that. The submarine landslide is in this region. I mentioned over there. So I'm going to focus on Fall League Bay and Baritory Bay. And due to time limit, I'm not going to show the details, but this is a very nice piece of work done by my former PhD student, Jiaze Wang. We published a paper on marine geology 2019. So Jiaze did a very nice periodicity analysis on the suspended sediment concentration, wind speed, and wave height. So to make a long story short, in those shallow Louisiana bays, the sediment transport is pretty much driven by wind-driven waves, okay? As I explained, every 3 to 7 days, here we actually have almost every 5 days. In Fall League Bay, we see energetic winds, which drive the wave height, which also drive the suspended sediment concentration. So this is a very nice matching between wind and wave and suspended sediment concentration. We also saw some tidal signal, 22-hour over here, which is which can also be seen on the suspended sediment concentration. So in another study area, which is Baritory Bay, we deployed 2 tripods, and this was based on the work by my master student Guandong Li. We actually have one new paper in press with ECSS. So if you zoom into this region, we actually have a really large coastal bay. It's called the Baritaria Bay. We deployed 2 tripods. One is at the BBN, which is Baritory Bay North, and the other is the south. We deployed 2 tripods during 2 different seasons. So here we have time series plot to show river discharge, the wind speed direction, wave height, the shear stress, as well as suspended sediment. So if you take a look at those 5 shaded areas from P4 to P8, wherever you have an energetic wind event, you have taller waves, you also have a spike on the suspended sediment concentration. And now if you look at the P6, 7, 8, again, high wind speed, high wave height, and high turbidity. So Guangdong also did a very nice periodicity analysis. And again, the whole story is about wind-driven, wave-driven sedimentary suspension. So every 3 to 7 days, depends on which period you analyze. So it could be like every 7 days or 5 days or 3 days, you can actually see the spikes on the wind and the wave height, as well as the turbidity. And then regarding the water level, it's mainly controlled by tides. Okay, so we have the tides over here, and the tide can also impact the turbidity with a very small spike over there. So after talking about the tripod bottom boundary dynamics, the last part of my today's talk is about human activities. So Louisiana is facing a huge land loss problem. I'm not sure if you know this, but about 90% of wetland loss is occurring in Louisiana among the entire nation. Okay, so if you think about all the wetland loss of the entire United States, the wetland loss, about 90% is occurring in Louisiana. So this is a huge problem. So in order to deal with the land loss problem, the shoreline retreat, people have been dredging both mud and sand in different areas. So over the past 7 years, I have been studying multiple dredge pit. Due to time limit for today, I'm just going to focus on 2 dredge pit. So one is called a pivotal channel, which is on the western Louisiana in a 10-meter water depth. Another is called the Raccoon Island dredge pit, which is just north of Ship Shoal in the intercontinental shelf. For those 2 pits, we will be looking at the long-term net accumulation, and I'm going to show you very, very high sediment accumulation rate. So here we have the bathymetric map of pivotal channel dredge pit on western Louisiana. So in 2003, about 1 million cubic meter of sand was extracted from this region. So this is a large depression. And you can actually see the scale. So the dredge pit is approximately 500 by 500 meter, and it's about 8 to 10 meters deeper than the ambient sea floor. So when time goes by, you start to see the sediment infilling and more infilling. And in 2016, the sediment filled up the entire pit. So if we look at the topographic profile from A to A prime, you can actually see the temporal change of the bathymetric profile. So this is back in right after the dredge, which is 2003, then 2004, 2006, 2007, and then we have 2016, which is the blue wiggles on top. Okay, so number one, very high sediment accumulation rate. This is almost a ½ meter to 1 meter per year. Remember, right next to the Mississippi River Delta, you have 5 centimeters per year of deposit. So this depositional rate is almost 1 or even 2 orders of magnitude higher. Number two, so when you think about the dredge pit, you would think that after long-term net accumulation, you should have a flat and a smooth surface. But our data shows that we have a very unique system. This is a muddy shoal. This is a topographic high with numerous mounts on top of the dredge pit, okay? So if we take a look at the detail, here is the dredge pit, and there are 2 regions. The north region is very flat and smooth, and then the southern part, we have numerous mounts, okay? And sometimes we just call those as mud volcanoes, okay? It's a very unique term. So this indicated that although we already have 100% infilling in this dredge pit, this pit is not in equilibrium yet. There's still ongoing consolidation and degassing after rapid burial of organic matter, water, gas, low density material. Lots of material will try to rise up to escape. And that's how you develop those numerous small features on top of a dredge pit. And those mounds are normally half to 1 meter tall. They are tens of meters apart, but this part is definitely very rough. It's not smooth. Now let's take a look at another dredge pit, which is Raccoon Island Dredge Pit. This is right north of Ship Shoal. Back in 2003, this is right after the excavation. This dredge pit is about 150 meter wide and 600 meter long. Again, is about 10 meter below the undisturbed sea floor. So this is a sizable dredge pit. When time goes by, 2 years later in 2015, you start to see the sediment infilling. And when you calculate the difference of those two bathymetry, you can actually see the deposition in blue. You can also see some erosional hot spots along the pit wall. And if we look at the topographic profile, this is 2013, this is 2015, and this is 2018. So if you calculate the sediment accumulation rate, the rate was about 1.1 meter to even to 1.4 meter, okay? So many scientists believe that when time goes by, the accumulation rate should decrease over time. But our study shows that in recent 3 years, between 15 and 18, we saw increased sediment accumulation rate. And this is possibly due to the contribution from fluid mud. And we also collected some geophysical data. So back in 2015, this is the side scan data to show low reflectivity inside the pit, indicating lots of fluffy mud inside the pit, mixed texture outside the pit. And this is the topographic depression, and this is undisturbed sea floor at the bottom of the pit. In 2018, when we went out collected geophysical data, the pit was gone. It's totally flat. This is horizontal, okay? And then regarding the infilling sediment, this is totally featureless because there's a lot of biogenic gas. If you look at the sub-bottom profile from U to V, from north to south, you can actually see a very flat seafloor, paleo river channel stratigraphy, very beautiful. Over here, you don't see much due to biogenic gas. And you can even see lots of bubbles in the water column due to the degassing. Again, this is due to the releasing of buried, the decay, releasing of the gas due to the decay of buried organic matter. Okay, so concluding remark. So I have covered a lot of different study areas, lots of topics, but to make a quick conclusion, so when you deal with sediment dynamics, you have to deal with the temporal and spatial skills, okay? That's very, very important. So in my view, there are top 6 major players you have to consider: river, the morphology, waves, tides, currents, and grain size. There are 4 stages in the river sediment dispersal in right nature hour diagram, but keep in mind the stage 2, stage 3 can be repeated many, many times before the final accumulation. Over the past 20 years, I have been studying sediment dynamics, and I believe that those are the key parameters we still need to quantify: settling velocity, erosional rate, critical shear stress. If you deal with cohesive sediment, the flocculation is very important, and you also need to worry about the suspended sediment concentration. When we deal with those numbers, we have to think about the range of the values, and most likely when you deal with settling velocity, it changes from 1 millimeter per second to 0.1, right? It changes order of magnitude. When you deal with the concentration, it also can change 1 or 2 magnitude. Because of that, when you calculate the accumulation rate or the sediment budget or sediment flux, you start getting a big, very, very big range, and normally 2 or even 3 order of magnitude. I think in the future, when we study sediment dynamics, one challenge, this is also an opportunity, would be for us to how to analyze the uncertainty and errors associated with sediment transport study. So this will be a very, very important topic for the future studies. Okay, so I would like to acknowledge all my students. So I have a list of reference used in this talk. Special thanks to my colleague and collaborator, Dr. Sam Bentley, who gave a talk last Friday. I also want to say thank you to my postdoc advisor, Carney Harris, who will be giving a talk on Friday this week. And then I also want to show a few pictures from my group, and this is our sediment dynamics lab. We have a few pictures from the field, and this is a collection of pictures from the SDL members. And at the end, I also want to introduce a special issue. So I'm collaborating with my 3 PhD students to organize a special issue on Journal of Marine Science and Engineering. And the title of this special issue is Marine Geological and Biogeochemical Processes from Coast to the Slope. And the end, go sediment, go tigers.
Great, great talk, Kevin. Thank you very much. So before I give the audience, ask a question, I know Tom Bianchi is ready. So I have a quick question. You can maybe answer shortly. So in the dredging pit, inside the dredging pit, the sediment, you mentioned it's organic rich. Anybody did the organic carbon analysis, the profile?
That's a great question. In fact, in this dredge pit, Raccoon Island dredge pit, we just collected 6 Weber curves. Okay, we are going to do organic matter content analysis. Dr. Sam Bentley's student already did some beryllium 7 and lead-210 analysis on some cores collected in an early period.
That's very good.
How
long of the core you have?
For the Weber core, the longest one we collected was about 4.5 meters, which was still not long enough to penetrate the entire pit.
Yeah.
But we were able to collect some cores back in 2015, and then we collected more into 2020.
Okay, cool. Okay, Tom, go ahead.
Yeah, hi, Kevin. It's nice to see you, and very nice story, very nice talk. I wanted to ask you something about sort of this movement of sediment from the inner shelf out or to the deeper water. And
this one?
Yeah, this one here. It's, how much of that do you think is from freshly deposited river material versus eroded sediment from marshes coming out of some of the bays? These shallow estuaries are very prone to wind-driven sediment transport. That's always been a big issue. Lots of disagreements about how much of that's getting on the shelf in the hypoxic regions.
That's a great question. So first of all, in our numerical model, we included the bays, but we did not include the marsh edge erosion. And that's actually one future work I plan to do in collaboration with multiple professors. So that's on our to-do list. So we basically only look at the reef suspension from the bay bottom, but we did not include any marsh edge erosion because the northern boundary of the model is basically like a wall, but we will be able to quantify that in the future. But regarding the inner and middle shelf sediment exchange, we have a pretty high confidence that we know the sediment is pretty dynamic, but we're not talking about a huge amount. We're dealing with millimeter level or maybe slightly less than that. And this kind of exchange rate is highly sensitive to the erosional rate we use. Because when you run the model, you can use a erosional rate from 10 to -5 to 10 to -3 kilogram per meter square per second. So that erosional rate will change this greatly. But we were not able to quantify the eroded sediment from the marsh edge, and that's a different scope.
Yeah, I guess just one other comment on that is that one of the other complicating things is that even if you are looking at bay sediment, open water, a certain fraction of that is old marsh material. So some of the old bay bottom is from marsh. And I think that's one of the confusions, is that some people think if you're just in the open bay, that's not really part of the marsh. But that's not true in this region, with so much loss and so much open water having been generated. Anyway, that's just a sort of another interesting complication of these open water versus marsh ideas. Thank
Yeah,
you.
I totally agree. If you talk about the ultimate source of the bay bottom sediment, they must be from the nearby area, right? So they
Yeah.
might be eroded decades or hundreds of years ago. They are deposited in the bay bottom and then they are transported offshore. So one challenge we have to deal with is that we don't know which one is the biggest driver, whether it's basically subsidence driven accommodation space you have to deal with, or whether this is offshore transport, a total loss of the sediment offshore. So I think that will be some future work we can focus on.
Yeah, thank you.
Okay, great. Gail.
Hi, Kevin. Really nice job. It was so nice to see that sort of history as of your work. And this is obviously an area that I am very fond of. And the background is just to the west of the box that you're showing there. But I think I'm confused. So the lower panel on the screen that you have up now, that orange is representing increase in sediment. So is that import of sediment onshore, or is it loss of sediment?
Okay, so when we initialize the seabed, okay, we have a total of 4 different types of sediment. We have the shallow water. Here, I define shallower than 5 meter isobase as shallow water. And then in the shallow water, I define mud and sand. In the deep water, which is deeper than 5 meter isobase, I have mud and sand. So we initialize the sediment in the model at the beginning of the model run. So after 15 months, we go back and then we track where are those shallow water mud located. So if they don't move at all, they should be all red or orange, shallower than 5 meters. Because I initialized my model domain like that. So what we found was that we found a small amount of sediment can go from inner shelf to the middle shelf. Okay, so we basically initialize numerous sediment trees, well, lots of tracers in the shallow water, and let the wave and river and current to mobilize the sediment. At the end of the model run, we found some sediment depositing in water deeper than 5 meters. So this indicates some shallow water sediment can be transported from bay and shallow water into the deeper water.
Okay, and the reason I'm asking is just that work that we had done earlier, we were seeing like strong onshore transport following cold fronts, and I wondered if this is part of what's being shown there, but I guess it's not.
Well, in fact, we also
really talking about the same thing.
Yeah. So Gail, I totally agree with you. In fact, my student Horan Liu made another plot, which is the onshore transport of deeper sediment to the bay. We found a significant amount of sediment depositing here from the middle shelf. So it's an exchange. It's exchange. We found that we did not include that in the paper because Horan's focus was on ship show, which is this region. Yeah, but we can do additional analysis.
So Kevin, followed up this. Quick question is, how deeper you think those inner shelf sediment can go into the middle or even a little bit out shelf? Here you show about 15 meters, 20 meters. do you think how far they can go cross shelf, go to a little bit deeper? How deep they can go?
Yeah, so again, I want to emphasize we're dealing with a log scale. Okay, so we only run the model for 15 months, which is slightly longer than a year. And this model is computationally very expensive. So we use 500 CPU to run the model for a long period of time. So it's computationally expensive. We can try to run the model for a longer period of time, but I recommend you to check another paper published by Zhengchen Zhang and George Xue, and they did some ROMS modeling computation for a 20-year period of time. So they also show some long distance sediment dispersal from the river mouth, from the inner shelf to the deeper water.
Okay. Okay, any other question from the audience? You can just go ahead, unmute yourself and ask Kevin. It's a great talk, Kevin. I think it's very, very, very interesting. And I think this coming Friday, Cotton Harris will also talk about some part of those Louisiana shelf in the Gulf of Mexico. So please mark your calendar and coming back the same time this Friday. So for the Cotton Harris talk. If no any other question, I think we can stop here. So any other question from audience? If not, you can stop here. Kevin, if okay, and let me know if we can share your PowerPoint to the community or not. Okay.
Sure, I already emailed you my PowerPoint.
Okay, so it's okay, right? So
yeah, no problem. Almost all the figures are from published papers.
Okay, wonderful, wonderful. Thank you very much. Again, this talk also available on the YouTube and the Chinese B station. So you can go back to rewatch that with the caption. Okay, wonderful. So have a good day. Okay, thank you.